I'm going to give you a little primer again here, just so you know. So a couple of weeks ago, there were some folks who were out like, what, 3 o'clock in the morning? Is that when you guys did that?
Yeah.
3 o'clock in the morning, and to get some observations of a star that you can only get at 3 o'clock in the morning. And by the way, it just gets later and later, so we're going to lose the opportunity, and we want to take a lot of observations. Anyway, power went out, right?
Power was good, but power had been out.
Oh, the power had been out, which means the computer was not connected up, which means you have to operate the telescope, and like I said, party like it's 1885. And so tonight we have Dave Sappington and Boris, and Tom is going to do some too. I'm not sure where you are, Tom, but Dave and Boris are going to talk about what they had to do in terms of celestial coordinates in order to try to find this manually. And then Boris is going to take us out and take a look at the 26-inch telescope and walk us through, you know, how to make that work.
Hot off the presses, and I didn't even mention my or Boris's name, but I'm Dave Sappington, and Boris Starosta is my colleague over here. I'm going to start the thing mainly, just go through some slides and maybe do a little bit of visual demonstration with these scopes, which the scope here is much smaller than that one and easier to kind of manhandle and show you what's going on. And then we're going to maybe adjourn to end there where Boris is actually going to operate a big scope. So you go to the next slide.
Yep.
So why do we do this? This is a super busy slide, but it lays it all out. I think about a year and a half ago, one of our members, Myron Wasiuta, suggested that we target a very tight double star with the 26-inch. If you look at the top left, this double star has a period of just under six years. So if we get a series of pictures over time, maybe we'll capture some of that orbit. But it is very, very tight. That little, actually I have a laser here. So the scale there, that's 1/5 of an arc second. You know, so for scale, that's probably, you know, 1/200th the size of the disk of Jupiter when you're looking at it. So really tiny and very close to the theoretical resolution of the scope in there. The scope is a little bit better than that, but it's tight. So if you
0.16.
Yeah. So to give you a feel for what it's like, I guess this is a video I captured. So if you just click once, Kevin, you'll see this is what we're dealing with, right? Yeah. Oh, okay. Well, it's usually a video, but I guess maybe it doesn't play too well. At any rate, the thing that you take away from that is it's a big, tight ball of photons. And from that, you can process. This wasn't actually used to produce this. This was an earlier thing. This was a more recent thing that I had, and seeing wasn't as good. But if you process a lot of those images and you take a video of on the order of a minute or so with anywhere from 100 to 200 images per second, so you're accumulating 1,000 or a couple of thousand images, you pick yeah, there you go. Yeah, right. Look better on my, yeah, it doesn't look that good. The takeaway is it's tough to see anything. As a matter of fact, it's even hard to focus on that. Yeah. But at any rate, if you post-process it, Myron actually post-processed some of the data that we did about a year and a half ago when it was actually a little bit further away. You know, here's one star and here's the other one. You know, he got some pictures like when it was about here. Right now, it's where that star is, which is, it's getting tighter and tougher to resolve. But by processing, picking the best images out of that and stacking them and everything, you could see distinctly, well, I don't know if you can see as much back there. What do you want, Mary?
So was the reason why the star was picked because its period is so short and it's optimally most visible to see, you know?
Yeah. So Myron said, you know, what can we do that probably hasn't been done before? So it's relatively tight and very tight in this case, and a period that is reasonable that we could image, you know, over much of the circuit. in 6 years, it's a fair amount of time, but it's reasonable that, we can make a dent in that.
It's right at the.
Yeah. So to Myron's knowledge and to mine as well, though he's researched it a little lot more than I have, nobody's done this with a scope. And as a matter of fact, if you look up delta Equulei, it's listed as a spectroscopic binary. So we know it's a binary just by looking at the light curves, the spectrum. And you don't usually think of it as an optical binary or, a binary that you split, but you can. So if you click again, you'll see a highlight when we're clicking. Yeah, right there. So this left or right side of the thing is just a big screen capture from Stellarium, the mobile version of it on a tablet. And this is the operative stuff. The coordinates, the right ascension and declination I'm going to talk about. The one on the left, upper left, is the current right ascension and declination because they change subtly over time. The one on the right is kind of the published right ascension and declination at a known time, in that particular case, 2000. I'll talk about that later in the deck, but I'm not going to dwell on it. And then as well, the altitude and azimuth, which I'll talk about. And finally, because that becomes important with what we are doing when the coordinate displays go out, the hour angle, which I'll talk about what that is as well. So if we go to the next slide. So this is one of the challenges that we deal with. And, as Kevin said, and Boris as well, that we were up at 3 a.m. A few months ago to look at it. Well, this tells you why. Now, obviously, this isn't to scale, but delta Equulei, the takeaway from here is think of the sun here and delta Equulei being way the heck in that direction. And so in February, you can't see it, right? It's more or less directly opposite the sun or directly in line with the sun. And so you can't see it as you come around here. And I've pointed out the morning and the evening sky. The Earth rotates like this and revolves and goes around the sun that way. So this is the evening sky. It trails the Earth, and the morning sky leads the Earth. So just after we have a solar conjunction with the double star, it becomes visible in the very, very early morning sky, which is tough for us astronomers, at least for me. So we caught it, I think, somewhere around here. I'm trying to remember when it was. It was like maybe March. So to catch it here, it is in the way early morning sky. So that's why you got to be up 3 a.m., 4 a.m. I think we imaged it all the way until 5 a.m. recently.
Yeah, it was into twilight.
Yeah, right now it's getting easier to see, because it's still in the morning sky. Yeah, but it's easier and easier to see. And in August, it'll be directly opposite the sun. So at midnight, it'll be as high in the sky as it ever gets. And then, kind of cycle repeats. But this gives you a notion of why we have to go out sometimes during the ungodly times. When we're in this area, it's going to be super early in the morning. Over here, I like to think of way late at night versus, earlier in the morning. And then as it goes over there, that's the easy part. It's, that this is the good part of the sky for people that like to be up in the evening and then beyond. So if you go to the next slide. So altitude and azimuth. Introduction coordinate system. That's why I brought my prop up here. It's about as simple as it goes, right? The altitude, this axis, the azimuth, this axis. Works pretty well, but there are some problems with that. The canonical mount is a Dobsonian mount for an alta-azimuth. But if you go to the next slide. So what are the pros of the alta-azimuth mount? They're mechanically simpler. Right, Boris showed you. Geez, there's really not much to this. It's got some bearings on there that can do it, and it's got a little lazy Susan on here. There's really not a whole lot to this. And even in larger scopes, they're inherently simpler. What about the cons? There's always cons, right? You know, otherwise everybody would have these. Well, the first con is that the altitude and the azimuth of a star as it traverses, as it rises, you know, and then eventually sets, is kind of a complex function of location and time. So it's not a simple function. You got to move in both axes. The star might move over here to rise. It might come up over here. I have to move both an azimuth and an altitude to track it, and then it might finally set over here. So it's inherently a little bit more complicated. Similarly, if you wanted tracking to track a star across the sky, you'd need something that was smart enough to move both of those axes at the same time. And finally, the telescope's field, what you look, if you have a camera on it and you're taking pictures, will rotate over time. And if you click it once and just click it, click it again here before we go on. This is the Big Dipper you might recognize in Polaris. So just imagine I'm taking I have this thing here, and I'm taking a picture of the Big Dipper, and this is my camera. So my camera doesn't do like this. My camera just stays like that. So if you click it again, Kevin, and just click through these until you got 4 of them on the screen. That's 2, 3, keep one more. Click there. So, you know, everything is moving around Polaris there. And so, you know, you saw the Big Dipper start there and comes around here. Well, here's the pictures you get. There's field rotation. So if you're imaging, your astrophotographers don't like that. It's kind of a pain. Now, I will say that for a long time, the largest telescope in the world was the Hale telescope at Mount Palomar in Pasadena. It was 5 meters. It's still in operation. It's a 5-meter scope, 200-inch mirror, and it had a ginormous and very specialized equatorial mount, which I'll get to. But every big telescope that I'm aware of since then has an alt-azimuth mount. And the reason they do that is because they're mechanically simpler. And they've got computers that can control the axis and do the right thing. And they got computers that have rotators to compensate for the rotation as well. So if you're going to have a big research instrument, you know, it's like back to simplicity, because it's much easier, especially if you have a ginormous telescope, to make that sort of mount versus another one. If you go to the next slide.
I did. Good question. So I used one of these once, and it had a digital thing on the bottom. So in other words, when it turned, it was kind of like a push to, but it had a
So oftentimes, what you see is, and actually the cast one that I have has that as well, though I don't use it. It's possible to have settings, they're called setting circles, or in this particular case, it'd be digital setting circles, something that actually measures this angle, right? So something that measures this angle, and similarly, they've got another sensor that measures this angle. And typically, when you have that, there's an associated little hand computer that says, that basically does the math for you. You tell the hand computer where you are. So, you know, this is this thing right here. You tell it where you are. You tell it when it is, and oftentimes they have an internal clock, so you may not have to do that. You may not even have to tell where it is if it's GPS. And then sometimes, if you don't do those, you can do a so-called 2-star alignment, which is similar. Basically, it tells the computer how this thing is oriented on the planet and with stars. And then once it's done that, you can, they call it push to, you can select a target, let's say delta Equulei. It'll say, you know, go left, go left, go left, go up, too far, go back down a little bit, you know, go right, and so forth. And then you're in it by looking at the sensors for the altitude, azimuth, and then doing a bunch of the computations. Well, you know, well, imagine just for the moment that we took that telescope and we took it to the North Pole and we set it up there. life would be great, because then, then, when we track a star, I'll put a little laser on here. When you track a star, the only thing that would move would be this. The North Star, Polaris, the North Celestial Pole, would be like dead straight overhead. But anything else, it just would move around like this. You'd only have to move one axis, right? So, and as a matter of fact, how you move that axis is actually pretty straightforward. It moves pretty much like a clock, There'd be like 24 hours to go all the way around, so 1 hour, 2 hour, 3 hours, like that. So wow, this would be a great thing. We could take all our jobs to the North Pole and life would be great. Oops. Okay, well, maybe not. We don't want to go to the North Pole. Well, so what's the next best thing? So let's go to the next slide. So just take that telescope and bring it down here. Now, I oriented it the same way on purpose. You might think that I would have oriented this thing going out like that, normal to the local horizon. But I didn't. I oriented it like that because so long, it was previously this pointed this direction and it spun and that one axis did everything we needed it to do. Now we just displaced it over here and we can still spin it and that one axis does everything we need it to do, except I'll kind of demonstrate this a little bit. Well, I can't because this one's on. But yeah, if you tilted this, you would get that effect, right? If I tilted it up toward the North Star, ish, you get that effect. Well, that's cumbersome to do, and fortunately, that's a thing. So let's just click one more slide, and before you do it, I'm just going to rotate this picture this way, because normally we think of the horizon as being level as opposed to here. So go ahead and go to the next slide. So that kind of represents what we're talking about. You're tilting that thing over. And, now your altitude becomes what will become declination, and azimuth becomes what will become hour angle. And if you click one more, you'll see that, well, that's what an equatorial telescope, equatorial mount is. It saves you the trouble of having to tilt that thing. So I'll move this prop out of the way. Yeah.
So if we could set this thing at 38 degrees, as you had it before, something like that, that would make it an equatorial mount?
Yes, and as a matter of fact, that's the segue to what you were talking to Larry about. The C-Star little robot automated scope is an out azimuth telescope, but it is smart enough and it's small enough that if you tilt it by 38 degrees, our latitude, 38 degrees from the horizon up, not from the vertical down. So 38 degrees from the horizon up, or 52 going the other direction. But if you tilt it that way and you tell the software that it is tilted, then it becomes an equatorial telescope. That's it. That's all. The only difference between an alt-az mount and an equatorial mount is basically the tilt of the azimuth axis, this vertical axis.
So Larry, how did you do that?
Well, I just bought a metal bar and bent 38 degrees. It's mounted, and you just mounted on that, right on the tripod.
Wow.
So it's pretty nice to demonstrate. It didn't, like I said, it didn't just tell simply what you're doing. And it says, okay, and people were doing that before, with that, before they had the software thing. They just told it, they were told it that it was at your fault.
Yeah. Yeah, so really all the software had to do was relax some of the constraints, because when it's tilted like that, you can actually point it below what it thinks is the horizon. If this telescope is, well, I'm not going to do it again, but if this is pointed up, then it's possible, this is normally, as far as it goes in the sky. But if I were to tilt this whole thing up like this, then there's more sky down below. So that's negative altitude, if you will, negative declination. And the C-Star wouldn't allow that before, but so the software says, oh yeah, when in equatorial mode, you can go past these limits. But in terms of tracking, yeah, it's just the same.
No, like, wow, same. You see the telescope.
Yeah, yeah. So my proxy for it is this, right? This is, so this is a mount that I got from Larry. This is one of our lunar scope mounts. I put a relatively inexpensive optical tube on that's very lightweight. And for the purposes of demonstration, just think that that direction is north, right? It's pretty close. It's like within about 20 degrees or so, but you know, it's pretty close to north. So, you know, you have your axes now. This became your altitude axis, was before, and now it's your declination axis. If this whole thing was up like this, right, that would be the alt-azimuth that we talked again, you know, when this thing is going straight up and down. But, you know, now we tilt it, becomes an equatorial mount, and we can move it around like this. Now, if we go, let's move it. I'm going to talk about this in a little bit more detail later on, but if we go to the next slide. So this is just describing what right ascension and declination are. They're very similar, if you think of it, to latitude and longitude on a celestial sphere. Declination is comparatively easy because there's a 0 point that makes a lot of sense, the equator. You know, you go just like latitude, you can go 10 degrees up from the equator, 20 degrees up from the equator, and so forth in the sky. And that's what this thing is. So this would be 0 degrees up from the equator. And that would be 10, 20, 30, 40, 50, 60, 70, 80, 90, right? You know, and that would be full up. So, so that's pretty easy because the 0 point, the equator makes sense. Right ascension is a little more complex, and it has to do with the fact that, well, you know, the stars, we said when we put the Dobsonian on the North Pole, you know, the star kept that same altitude, which became declination, depending on, you know, regardless of where we were spinning it. Not true for the azimuth at the North Pole or right ascension elsewhere. So we have to pick a place in the sky that is going to be 0 right ascension. And what we do is we pick it at what's known as the vernal equinox. That's when the sun, it's basically the first day of spring. A little bit more precise than that because it's more than just a day. But you know, when the sun transitions from the southern hemisphere sky to the northern hemisphere sky. And another thing that you might notice is declination is measured in degrees, just like latitude, you know, 0, 10, 20, and so forth, all the way up to plus 90 at the North Pole or minus 90 at the South Pole. Whereas right ascension is measured in time units. And it kind of makes sense because this thing is going to be spinning to track a star. This thing spins around. Basically, it will complete a full circuit in 24 hours. So instead of degrees, you can think of like 0, 1 hour, 2 hours, 3 hours, 4, 5, 6, and so forth. That's how you do that. Go to the next slide.
Just quick. So
Okay.
That's why that thing that's on the big telescope there is in, when the big bar is in hours. Is that what it is?
Yeah. So I'm going to talk about that, but yeah.
All right.
So if you were astute, you noticed I put asterisks in various places before this, saying that the altitude at the pole or the declination doesn't depend on time. Well, that's not strictly true. There's a very subtle variation associated with the Earth's wobble, but it's really small. It's really small. The wobble, you know, think 1 degree over 70 years. So I mentioned this in an earlier talk that Tom and I gave several months back, and this is a slide from it, but suffice it to say that you can switch between what are known as epochs. you know, the situation on the ground in the year 2000, the coordinates were one way, and they've changed just a little in the 25 years since then, you know, maybe a third of a degree. So they're subtly different. And so we often see J2000 and J now. J, you know, J is the epoch, and now just means current time. And the most astronomy programs freely compute these on the fly, you know, on the fly. The coordinate displays on the LMO telescope display in J now, so it's something to be aware of. If you go to the next slide. Okay, so this is the question that kind of Kevin was talking about. This is what you have vis-a-vis coordinates, dials, displays on the 26-inch. You got this thing up here in the upper left-hand corner, which gives you the local sidereal time, which I'll talk about a little later. It gives you the hour angle, which I'll talk about a little later. It gives you a tangent arm reading, which I'll talk a little bit about later. There's a common theme here. RA and declination I actually have talked about, so those would be somewhat familiar to you. So this display here is generally very, very helpful. Sometimes it's a little bit off, and we discussed this in a talk that we gave several months ago, Tom and I, and the short answer is it's not off by very much. It's off by, it can be like a field of view in the lowest power eyepieces on the order of less than 10 minutes of arc typically.
That display's only been available since 2000.
Oh yeah. So this scope was built in 1885. So they did not have LCDs with computers behind them in 1885. So this is a relatively recent retrofit, even though it uses like 1970s, 80s vintage hardware. I think it was put in 2007. Yeah. On the other hand, this other stuff is vintage hardware. And so what you do see is, and we'll see these when Boris shows us the big scope out and thing, we see the hour angle, which I'll define here on the next slide. And we have, so you can read off the hour angle, which basically is where the scope is pointing in one direction, and a declination scope. Now, you can't really see it on this thing here, but this thing has similar setting circles where this would be, you can see a silver ring here, and what you probably can't see here, there are gradations on that. This would be analogous to the hour angle, and when we move around here, there's a little, let me see if I can show it to you here. You can maybe see this little indicator that shows you where you are on the hour angle thing, just like that thing does. Similarly, let's see if I can, well, have to move it around this way. There's something on deck as well. So there's a set, these are setting circles, and it shows you where you are in deck. And on the 26-inch, it's a little harder to deal with because the declination display is way the heck away from you. This hour angle thing is a really big honking dial you can see from the floor just by looking at it. The declination thing is on a setting circle that's way up, very fine things, and you actually have to use a telescope essentially to look at it.
Image is found in the mirror. There's a mirror here.
Yeah.
So this declination periscope looks into the mirror and sees the.
So at the business end of the telescope, there's this thing right here. Here's the finder scope. Here's obviously the business end where the main objective forms an image. And this is the declination scope. You peek into that looks into that mirror, that has a little light shining on this ring that has gradations on it. And that's how you figure out what your declination is.
Of course, on this, so if I went to Stellarium, this star is in this location, this right ascension, this declination. You're telling me that I could use the dial here and find it?
Yeah, you have to set it up right initially because our angle, you know, this thing here, that's why this thing can be moved, but you'll do an initial setup like that, and then yeah, you can do it.
Wow.
So, and that's, you know, people used to do that, and I'm sure Boris probably did something similar on the 26-inch back in the day when you didn't have the LCD
You
display.
don't have to set anything on a 26-inch because the only readout you have,
Oh,
is hour angle.
Oh,
There's none to reset here. The
Oh.
reason you said this is these gradations are right ascension.
yeah, these are right ascension, these are declination.
It's not, I mean, it can be used as an hour angle,
Well, it is measured in hours and you
but
can
it's
set
measured
it.
in hours.
Yeah, you can set it so that zero, you basically can control it.
Yeah, but this is designed so that if you're looking up a star or something,
Yeah,
and it says in the booklet, this is at 23 hours, 15 minutes, right ascension. If you don't know sidereal time, you're gonna have a hard time figuring out where that is in the sky.
exactly. So next
So-
slide.
So this
Give me another
This will help.
assist to Boris. Thank you, Boris.
and most amateurs will not have had a sidereal.
So yeah, this thing doesn't read right ascension. It could be set to read hour angle. So what is hour angle? So going back to our scope here, hour angle for any given target in the sky, let's say that thing is over there. Hour angle is the angle from the target to the meridian. The meridian is like a line that goes from due north across the zenith to due south. So things over there are east of the meridian, and the angle is the hour angle. These are hour angles east of the meridian. Over here, these would be hour angles west of the meridian. And this is that same picture that we showed before from the scope, where you zoom in, and the gradations here are precisely that. Here we're showing 1 hour, 2 hour, 3 hour, 4 hours. So this is 2 hours, and these gradations are
5 minutes.
5 minutes. So that's 2 hours, 25 minutes, hour angle. Okay, all right, so we're getting there. We have hour angle, we have right ascension. We're almost to what we need to have. So if you go to the next, well, actually, with modern stuff, that's all we need, because the stellarium will tell you the hour angle at any given time. But if you didn't have that, you would have to go to the next slide, which talks about sidereal time. And if you just click once, you just click once and then you just wait. And I shouldn't, badness on me for including a movie here, but this shows the difference between what is known as sidereal time and solar time. We normally think of 24 hours in a day from one day to the next. And you really think of that as, when is the sun going to be directly overhead? 24 hours from now, it'll be directly overhead again. 24 hours from then, directly overhead again. Well, the Earth is going around the sun, right? So the Earth started here. So by the time 24, and this is exaggerated, obviously, by the time the Earth has moved up here, it can't just be pointed this, it has to point down a little bit more than that. So that gives rise to this, the solar day, which is what we think of in terms of 24 hours a day, versus the sidereal day, which is basically how fast the Earth rotates with respect to the background stars. And since we're interested in finding background stars, sidereal time makes a lot more sense to use in this particular case. And that's 23 hours and 56 minutes. And if you think about it, you take those 4 minutes that it's shorter than a day, and you multiply 4 minutes times 365 days in a year, that will be another day. So you basically have 366 of these sidereal days to be the same as a 365-day solar year. If you go to the next slide, finally, how do you relate these two? Well, this is it right now. I don't need to go over there. So basically, we talked about how we get out, what hour angle is. That's something that we read on the machine, or not read on the telescope. That's the setting circle thing. Local sidereal time, I'm told that there used to be, Boris would know more about this, some sort of grandfather clock-ish thing that kept sidereal time.
Looked a little like that one.
Yeah, okay.
It's bigger, kind of like that.
So if you had local sidereal time and you had right ascension, because that doesn't change, precession nutation allowed for, doesn't change, then you can just compute. You can do a little bit of algebra here, and you can see the hour angle is just the local solar time minus the right ascension. And so, yeah, you just needed this, a table that says the right ascension. That gives you the hour angle. You can stick that, move the scope to do it, to take you there. Now, a couple of the things that make moving the scope a little bit more complex than that is, first of all, you can freehand the scope along both axes. You can unclamp them and unclamp the drive motors and freehand it. So you can do like this. Well, when I'm moving this scope up like this, I can still do like that really easy with my hand. But when that scope is in a position more like this thing is 20 feet in the air, as is this. And it's not so easy to move around like that. Furthermore, while you can engage motors to slew in the hour angle or a slew in right ascension, so you can engage a motor to do this, there is no motor that you can do coarse movements in this direction. There is that so-called tangent arm that I mentioned briefly, but it can only move on the order of a couple of degrees. So what we often do, if we have a target and a particular declination, is we need to spin the scope in RA to get this thing down to where we can reach it by hand, and then move the declination to about where we need to be. And if we have to spin this thing a little bit down to keep that thing low to the ground, we do. So we basically get in the ballpark within a degree or so of declination, or at least I do, when you're on the ground. And then once you're happy with that, then you can slew up and right ascension to wherever that target is. And then once you clamp the axis, if you missed the declination a little bit, you do have a little bit of play here that you can do with. But that's basically how this 26 cents operates. That's, if you go to the next, that's my last slide. So I kind of like segue into,
Yeah,
if we
we'll go demonstrate that.
go and
We're
bush.
gonna take all this stuff.
Try to take all this stuff with us.
Oh,
we
okay.
can have the camera there too.
Okay.
And
All right, I can carry the camera. And this right here is that hour angle circle that you saw on the slide that shows the position of the star. And right now, gosh, I didn't bring a bright light, but it reads 4. So right now we are 1, 2, 3, 4 hours to the east of the meridian. And I want to get it to come down here. I want to use the telescope. So there's a clamp for right ascension. Now we're not partying exactly like 1885, because in 1885, I'm not even sure if they had stowed the scope this high, they probably would have wheeled the chair around, because the clamp was a hand crank at the tailpiece.
Oh.
It would have been a hand crank. But when I was working in the 1980s, that clamp was already electric. That's probably the exact same motor and everything.
I should point out this thing here just because it looks so cool,
Start with the clock drive.
which is the clock drive, the governor and the grandfather.
Come around and look at you can look at it from either side. Oh, sorry. So as Dave was saying, this whole thing works just like a clock. It's like a 24-hour hand of a clock, or I should say, it's like the hand of a 24-hour clock. If you left the drive running all night long, and if there weren't things in the way, this whole tube would roll around all the way around 360 degrees plus 4 minutes or whatever, or plus an extra degree in one day. So it's just like a big clock hand. And in fact, it functioned back in the day just like a grandfather clock. The clock mechanism was driven by a weight that slid down. It was connected on it. It was on a chain. I don't know how heavy this weight was. It must have been a couple 100 pounds. And it would come down this slot here and would keep going down and went down. I don't know how far down it went. Now, you know, a grandfather clock at home, you have to raise, I don't know, this is really old technology. Maybe I'm dating myself. With a grandfather clock, you have to raise the weight. You're putting energy into the clock, potential energy by raising the weight. And then over the course of a week, that weight will slowly come down. And I think most grandfather clocks, you wind them up like that once a week. Anybody know any better than I do? Because I'm not sure. I've never had one. Well, this is a bit heavier than the average, like hour hand on your grandfather clock, which might have weighed a half an ounce or something or less. And so the amount of energy required to turn this thing like a clock hand is a lot more. It's a lot more energy. And that's why it took this heavy weight only 90 minutes to go from the top all the way to the bottom. And we actually still have a similar limit in terms of the electric drive. It's a 90-minute limit because the axis is actuated not through a complete gear, but through a sector. In other words, just part of a gear. And after 90 minutes, you run out of gear. So every 90 minutes, you have to reset that. And that's how I am intuitively deducing that the weight came down in 90 minutes, even though I'm not really sure. Anyway, now we've cleared how this thing was driven back in the day. Nowadays, we have electric motors. And we would have unclamped the right ascension axis. And now we have an electric motor to so-called slew in right ascension, which means east-west. And I'm going to go slew to the west. That is, the objective is going to go to the west, and the tailpiece is going to come down to me in the east. So I push the west button, and it comes down to us. And as Dave was saying, when we point the telescope, we don't have this kind of a motor in declination. So you set the declination manually always. You have to move this, you have to slew the scope by hand in declination. Which is this axis, movement in this axis. Because the declination axis, the axis that it turns on, is this shaft right here, the shaft that the counterweights are on. So that's the north, that's the axis that if you want to move the telescope north or south. So I want to unclamp that. To show you how it's moved north and south. So right now I'm moving it to the south, even though I'm walking north. And because we don't have a motor for doing this movement, you definitely always want to do this first. Because if you make the mistake of looking up all your coordinates and then using the motor to slew it east or west, and it goes very far east or west, or east, I should say, or either way, you might find yourself in a position where you can't even get to this thing anymore. And then you have to wheel the chair around. And once you're on that chair, it's very hard to actually move this in declination because it's heavy. And it's kind of a, it's, you know, the chair is a little bit of a, the chair is 100, how many years? That's like the original chair, 1885. It's a little bit like the Cyclone roller coaster at Coney Island. Who's been on that? Gosh, we have a dead crowd today. Nobody's been on the Cyclone at Coney Island? That is a scary ride. And the whole reason it's scary is because you're on wood. And it's really violent, too. There's no smooth motion on it. You just get thrown around in that car. So I rode it once, and that was enough. So once we have set the declination, roughly by hand, then we can use slow motion control motor. And I can point out where that's located. Nobody over here is going to see it, unfortunately. Dave was talking about a sector arm. So there's this triangular looking contraption here on this side. Actually, I can make this go that way again. Bye. Don't go too far. Okay. So there's this triangular contraption here. that is connected to the declination axis. And there's a little motor right there, that silver box, that turns a worm gear, and that causes this sector arm to move up and down like that. So this is the amount that we have motorized. This is the amount of pointing range that we have. So once you set the declination roughly by hand, and you lock it in place, pushing that button, then you can make adjustments north or south with electric motors like this. You can hear it. Right, I turn north a little bit. I want to make it come back down towards me now. Because I forgot to describe, when I move it manually, how do I know what declination I'm set to? This whole demonstration is how do we do it without this display working? So that night, I don't know, was it a month ago or 6 weeks ago, we were here. The power had been out. Power was back on again, and all these motors were working. But what wasn't working was the readout. You know, we couldn't read right ascension and declination or any of this other stuff. Sorry?
Struggling to read.
Well, well, I'm going to get to that. So, and everybody's going to have a try to point this in declination. It'll be fun. So the declination ring is up there. Okay. People are going to have to scoot down here to see it. Or you can remember what it was like on that slide. But you see that little mirror right there?
It's easiest to see from that side of the telescope.
There's the mirror. This is the ring right here that got a brass inlay, and the brass is etched with very fine markings for declination, north and south. And that is red. You see inside the mirror there is the image of that brass lit up by a little light bulb, a little white light bulb.
You can see the light.
And we read that ring through this periscope here.
You can see the light from this side. You can't really see the light from that side
You
of the
can just
scope.
see the light in the mirror.
Or yeah,
See the illuminated declination ring in the mirror.
And then you actually look through this.
So yeah, so I forgot to bring a light. I didn't bring
yeah.
or actually I do have my lights. Maybe
Anybody have a
they're in the
flashlight?
the other room now. Bring this down a little lower. Everybody can have a try. So this is just like a submarine periscope, sort of. You just put your eye right up here, and you can see there's gradations and numbers and so forth. Now, what's really funny is 6 weeks ago, when I was trying to point the scope with using this old stuff, I realized they probably hadn't cleaned that mirror in about 20 or 30 years. Or the ring. And it was nearly impossible to read any of the gradation. It was a combination of guesswork and
This might work.
now we've had it cleaned. Sorry?
You actually found a tiny double doing this?
Yes, that's how we found the double. We did the coordinates, the declination coordinate in here,
I couldn't read.
and then locked it in place. And of course, we figured out the hour angle from the sidereal time and the right ascension coordinates. So what Dave didn't mention is there's an interesting it's not quite a definition of right ascension, but
Yeah, that's
it's
what we're
close.
trying to do. I
When you
forgot to bring
see
one.
a right ascension listed for your object, say for M13 or whatever you want to look at, that right ascension, that is what the sidereal time is when that object crosses the meridian. So I can tell you right now, sidereal time right now, according to this readout, is 12 hours and 25 minutes. Right now, objects with a right ascension of 12 hours and 25 minutes are crossing the meridian. So that way I know that if an object is at 13 hours and 25 minutes, it is going to be, okay, students, how far east or west is it going to be of the meridian? The object that is at 13 hours and 25 minutes. Anybody? Sorry, what? It's going to be 1 hour to the east, because 1 hour from now it'll be 1325, and that will be the right ascension. So if I have an object right now at 1326, right now, see, time advances, I would want to point this to 1 hour east. And I'm reading the 1 hour right there. The paint is a little worn down. But that's how we did all our pointing back even in the 1980s. We used the declination periscope, which is very, very accurate. And then we used the hour angle, which is kind of rough. But what we would do is, as long as we set the declination accurately, to find, this is for finding parallax stars. We were making photographs of parallax stars. Once you had the declination set, you might have to swing back and forth a little bit to find the star field that you wanted to photograph. Because in right ascension, our pointing was not that accurate. Because of that, that's the accuracy we're getting, which is not. You would have to do a meridian flip for objects that are, let's say, pretty far north, right? So if you had an object here and you're tracking along, you're tracking. Well, eventually you're going to run into the pier. That's not good. If you wanted to continue to observe it into the western sky, you would have to flip the telescope over. However, that is not being done anymore. Not allowed, not permitted. Because of all these wires
This looks pretty
and
cool.
all this stuff, they don't want it to be dragging over the axis.
Oh, yeah,
So-
there you go.
I don't know when the last time was that there was a meridian flip. I never did one, even in the 1980s. Who did it?
Tiger beam?
One time, 20 years ago.
Oh, he did? What, just to demonstrate it, or was he going after something?
Well, we were looking at
Oh, okay.
over in the north. Oh, let's look at that. It looked like Mars. Pretty incredible.
Right.
So Boris, you could point out the things that you discovered, I don't know, several months ago, the high precision right ascension metrics that are on the other side?
Yeah, so some time ago, I've been climbing all over this thing just because I like heights. Isn't that right, Dave? I did discover, I'm not sure, they must have used, maybe if they had an assistant, they would have done it this way. There is actually a high precision hour angle circle right here. Now, if you look right there, when I'm pointing this light, you will see a little magnifying glass. And actually, there's one on the other side too. There's one on each side. And we were up there looking through there, and we discovered a very finely engraved. In fact, it's so finely, it's actually got a vernier, for those of you that use calipers. It's got a vernier scale, so that you can get down to I don't know, what was the accuracy we decided?
5 arc seconds or something insane?
Some
like that?
insanely high accuracy in terms of hour angle.
Like 100 times more precise than
Yeah.
what you read on the other things. Yeah, well, that's the thing. To use that, you got to have somebody up there.
You have to get, that's where the grad student would be.
Yeah, so you have to have your assistant.
Well, that would be the undergrad student.
Oh, the undergrad will be up there.
Yeah.
Grad student
Would
would be down
would
here.
the undergrad be up there on the top?
Yeah, they're dispensable.
Cranking the dome by hand.
Yeah, that was a neat discovery. So we've been discovering some neat things about this scope in recent explorations.
Let me
Yeah.
point out one other thing, which is that if you put the scope absolutely vertical, then you're going to be exactly at an hour angle of 0,
That's right.
and you'll be exactly at 38 degrees declination.
That's right. So Tom was saying that pointing straight up gets us to hour angle 0, which should be pretty obvious now to everybody, because that meridian line goes through the zenith, which is straight up. What's slightly less intuitive, but nevertheless true, is that pointing it straight up is plus 38 declination, which is the exact same latitude that we're at. And in fact, this is how it's stowed. We stow it at plus 38 So the first thing we do when we close everything up is we put it straight up and down. We might even read off, oh, look, I'm at 3831, so I guessed pretty good. It just always gets stowed in the same position, more or less. I'm not sure why that would be good, or maybe that's good for the scope, I don't know. Sorry?
Consistent glance sag.
Consistent lens sag, yeah, but I don't think there is any lens sag. Oh, yeah, a long time.
One more quick announcement.
Yeah.
The 8-inch, if anybody wants to take one of those telescopes home, now is the time to think, otherwise we're pack it up and give it away. Take it up. Yes, sir.
Last call on the 8-inch Dobsonian, both of them.
New guy right here.
Okay. So I think, Barry, you had a question? Yes.
Has it ever been re-engineered or this is what?
No, it's the way it is. And in fact, what I learned from Ed Murphy recently too, is that this is a mount made by Clark. And this is the largest telescope in the world that is both a Clark telescope and mount. It's Clark through and through. And there's no other telescope of this size that's like that. That's operating. For example, the sister telescope up at the Naval Observatory, which is the same size refractor, also made by Clark, has a different kind of mount, not made by somebody else. Sorry?
Hey, Boris, you should like move the dome, just gratuitous.
Oh, shall we move the dome? That's a good idea. Let's move the dome. So again, back in the day, partying like it's 1885, there's a motor up there that wouldn't have been there in 1885. There's still a hand crank up there though. You can see the hand crank turning. It's turning. Now here's a really neat thing. If you don't look at keep the dome going. This is fun. Keep it going, Kevin. This is something that I find very amusing. If I don't rotate the dome a lot, sometimes you got to rotate it a whole 180 degrees because of the way the shutters are split up.